Okay. All right. Today's lecture is about 50% repeat from what we've done before. And the reason is because this information is going to show up on tests, quizzes, and everything else, and I want to make sure we go through it twice. This set of slides, actually, I got from the Silicon Labs instructor site, which is actually is a little bit more complete than the one I think last time I was using the book when I went through this, so I'm going to kind of go through the slides, because this set of slides actually has all the instructions in great detail that's there. So it'll probably be a fairly, not a real long class, but that's there. So I'm going to go through the instruction sets again, and probably 2/3 of the time we're going to spend is talking about the addressing modes again. We talked about them before. This is the repeat portion of the class, and we've got, as we look at it, 1, 2, 3, 4, 5, 6, 7, 8 different addressing modes that we're going to be going through that there, and then we've got 5 different instruction types. Now, as we look at the instructions, we're going to find that most of the instructions, there's only a few, but there's a long list because the addressing types affect that there. So let's just kind of go through that there. Basically, when we look at the 8051, it's just like when you had the 8086, every instruction is going to be broken down to an opcode, and that's 1 byte, followed by 0, 1, 2, or possibly 3 bytes of that are needed to fulfill the instruction that there. Actually, this particular processor is 0, 1, or 2 bytes of operands. So the format is basically going to be the opcode itself, whatever that is, followed by the data that's needed to perform that opcode. That there, and we'll look at the instructions that there. We're not going to be looking at this in the way that we do in great detail, other than the fact we need to look at that there. The operand is what is the data that we're going to be working. It could be the data value itself, if we're using the immediate mode. It could be a CPU register. It could be a memory location or an I/O port. Those are the 4 values that you're going to see for the operand. And if it's the data itself, that would be 8 bits. If it's a memory location, it could be 2 bytes, 16 bits. If it's a register, it's probably not going to be any. That's going to be 0 bytes for the operand. An I/O port will be 1 byte. So depending on which addressing mode, it's going to determine how many bytes we need for an instruction. The format is reverse of what you would think. The first thing is fairly clear. That's the instruction itself. The instruction itself is the first thing that you see, followed by the destination. Now, this is where things get a little bit interesting right here, is that our data moves from right to left. It goes from the source to the destination. I welcome that there. I don't start having people tell me their name as we walk in, so it becomes part of the recorded record of whoever's late for class. That's there. So that's there. So, but our data moves this direction, from right to left. So unless you're reading in Arabic or Hebrew, that's a little unnatural. That's there. Those are the only two languages I know that read from right to left. Chinese and Japanese read from top to bottom. No, wait, Chinese reads left to right, left to right or right to left. Top to bottom, so it reads vertically. So again, the only two languages that I can think of off the top of my head that read right to left are Arabic and Hebrew, right there. And since both those languages come from the same part of the world and they're from the same basic root, they're both Semitic languages. That's there. But this is the way that it goes, and that confuses a lot of students when we look at it there. Now, here I'm going to go into a little bit more detailed, and I'm going to sit down for this simply because when I went through this yesterday, I stood and pointed that there, but since I'm recording this, I'm going to want to use the marker here. So, all right, the top half of this right here is the basic CPU. This is the top half right there. The ALU is the arithmetic logic unit. That's what does the adding, subtracting, everything else. Now that's fed directly into it is the accumulator. You'll find that a lot of our instructions, such as add, multiply, divide, some of those instructions have to go through the accumulator. The accumulator, and that's actually register A when you're writing assembly language, is called the accumulator. That's our primary register. Then we have over here our B register, which we use on occasion. That's just another register there. And then over here we have something called the stack pointer. Now the stack pointer points to the stack. Now the stack is a location in memory that's used for what I would call post-it note type data. Things that we want to keep there, but not for long term. The most common use for the stack is used for posting, putting addresses on a interrupt. Whenever an interrupt is called, the microprocessor has to know where to go back to. So whenever an interrupt is called, service routine is called, and we'll be dealing with those in the next few weeks, the processor will automatically push onto the stack the program counter. Now the program counter is down here, right here. This keeps track of your current location in memory, right there. So as we execute an instruction, the program counter, and we also have something called the program counter incrementer. Now the program counter incrementer, its job is to look at the instruction that's being executed, the opcode, and it knows whether there's one or two bytes that follow it that need to be skipped before it goes to the next instruction. Because our code's going to look like this, and I'm just going to make these numbers up. It doesn't really matter what they are. But let's say I want to move into A the number 23 hex right there. Now I don't know what the opcode is for move A immediate data. So I'm just going to make up a number. We're going to say it's B0. If I want to take the time, we can look up the opcode. But what that's going to store is in memory. It's going to store B0 23 right there. Is what it's going to store in memory. Oh, and right there. So the program counter is counting, and right there, the program counter is counting here, and it needs to skip this instruction. So it has to add not 1 to the program counter before it does the next instruction. It has to add 2, because the next instruction is going to be here, right there. So that's the job of the program counter incrementer, right there. Is it has to know, it updates the program counter with what the next address is, and that varies with what instruction is being operated. There. Now, fortunately, as a user of this microprocessor, we don't get into the internal workings of it very often. This is probably the only time I'm going to talk about the program counter incrementer, right there. We also have something called the data pointer, and the data pointer basically is used to point to data for indirect addressing. So we'll talk about the indirect addressing and some of the instructions for that, and the data pointer is used for that. And we would preload that with the address of the start of our data. And normally that would be used if we have a string or an array of some type or a lookup table. We would use the data pointer to point to the start of it, and then we would increment the data pointer or provide an offset to it in order to look at our data. We've got this buffer in here, which is just a buffer. It's a location for storing data, there before it goes in. We got our program address register right there. That just keeps track of where our program starts there. Then we've got this pipeline, which I'm not going to get into. That's basically for moving data in and out around there, going from that there. And then, of course, the data bus goes through all this here. We got our logic control. Our logic control basically is used for our reset and our clock to keep track of things. And then our power control register down here is how we can tell the processor to go and to either stop or to idle out there. And that's used to save battery life. And I think everyone who owns a cell phone today is fully aware of how important battery life is in microprocessor-based systems. The ARM processor that your cell phone uses also has a powered down mode or an idle mode in order to save battery life. Otherwise, if that processor was running full speed all the time, while it's sitting there on your shelf, you're going to get about 3 hours before the thing goes dead. And typically, the average cell phone lasts about 12, 14 hours, depending on how much you talk and surf on the web. But this is used to save battery life, is these stop and idle modes. Over here on this side, we've got the special function register bus interface. We're going to talk a lot about special function registers. We're going to be doing a lot of discussion on special function registers. Going back to the top, we've got our 256 bytes of static RAM and our addresser for the static RAM that's built into it. Now, our processor we have has far more than 256 bytes. I'm thinking our processor has like 2 or 4K. I can't remember that there. Off the top, there's so many variations of the 850 that there. I can't remember exactly which which one we're using that there. So this is all part of the core. Now, the special function registers vary with processors. We'll look at it in more detail. The memory interface, that's to connect to the outside world. Now, in our processor, some of the outside world memory is internal to the processor. That makes this processor a little different when we look at the 8051 shell like this here. This is just a standard 8051. Our processor is going to be a little bit different because we've got the memory on our chip that's on the chip. We don't have to add to it. We don't have to do any wiring to it, but we have to treat it in software as if it's outside the chip. That's there, and that's very easy to do. We'll see that there. And then we've got our interrupts right there. And interrupts, you talked about in your 8086 class, but an interrupt is basically a request from an outside device or function, and it doesn't have to be an outside device. The timers are considered outside devices to our core. Even though they're on our chip, they're still considered, and they will generate interrupts. That's how we normally use our timers there. So that's our basic core, and as we look at the processor. So now as we look at our memory map here, this is for a 1 for the 8F20. Ours is the 8F850. It's very much the same. Silicon Labs, they all use the same basic memory map. The only thing that differs is the size down here in terms of the memory map. That's a little bit different. Some of them have 8K of XRAM. Some of them have 2K of XRAM or 4K. This XRAM here, this is memory that's on the chip, but you treat it as external, right there, external. And the reason we treat it as external is because the 8051 core only would address 256 bytes. So they use the external address base, which is 64K right there, for addressing. Now the 8051, as we're looking at this, has 3 different memory address locations. That's there. The 8086 only had 1. Program memory goes from 0000 all the way up to 1007 on this particular processor, right there. This is our flash programmable memory. That's where our code resides. Now we also have some scratch pad memory here that's only 7 bytes. Not 7 bytes. That's 7F. That goes to not quite 256. It's half of 256, 128 bytes right there of scratch pad memory that we can use up there. So, but this is program memory. Program. This is our data memory. Now, the special function registers right here are also part of the data memory right there. Most of what we're going to use is probably down here in this range because this is the largest block of memory we've got right down here. Because as you look at this here, we've only got 128 bytes and they're shared with the special function registers. And because of the way the silicon labs and most of the modern 8051 manufacturers have added more and more devices to their chips, such as timers and analog to digital converters and all these other things. Those are controlled through the special function registers. So really, most of this 128 bytes is not available to us right there. So a lot of what we're going to be doing is using the external memory right there. That's there. And again, this shows that we have these off-space RAM. The chip we've got, we can address that, but it takes up so many of the pins that you would never use the chip we're using with external memory. It's only got 16 pins. You need 8 pins just for the data bus. Another 3 pins, you've lost over half your pins because you lose VCC and ground. There's 2 of your 16 pins gone, so now you're down to 14. You take the 8 for the data bus. Now you're down to what, 6? You take 3 more for the control lines. Now you're down to 3 pins left for any kind of control applications. So the chip we're using, you would never use with external memory. The only memory you would use is what's on the chip itself, right there. You would never add additional memory to this particular microcontroller. The original 8051 was a 40-pin device, and it was very easy to add additional pins. Now, some of the 8051s, that, the one that I'm talking about in this slide, it's got 100 pins, and it actually has more pins. So you can actually use external memory with some of those that there, and they're all from the same family. They use the same compiler, the same interface, the same programmer. It's just a matter of what your application is that there. Our application is just to learn the chip and learn how to interface to it. So we're using the cheapest and the smallest we can get away with, right? That there. So, all right, here's our internal data memory, right there. And as you can see, we've got here, we've got these 3 banks right here, 4 banks, excuse me. These are our registers R0 through R7. There's 8 bytes each, right there. Now, before we can use those, we have to specify which bank we're going to use. If we don't, it uses the default. So for our first series of programs, we're going to worry just about the default. We won't worry about setting the bank. But these, we've got 32 bytes of memory there that are addressable by just the registers right there. Then we've got a series of memory locations here. And I didn't count this, but it goes from 20 to 2F. So that looks awfully a lot like 16 right here. 16 bytes right here. Right here. That are bit addressable right there. They're bit addressable, so you can use set bit and clear bit with those right there. So, and to be honest, I don't use much memory that I use bit addressables. I use bit addressing with ports more than anything else, or special function registers. And then we've got another block of memory right here that is just general purpose RAM. So we'll probably use these for most of our lab experiments for right now, right there. It's a little easier to use that there. Now, as we get to the top part of this right here, we end up with our special function registers right here. And as I said, our particular microprocessor uses almost all of them right there for that there. It goes from 80 to F8. So not all, beyond F8 you can use, but that there. Because again, we're getting into this area here. But these are our special function registers. Each one of these bytes along this right here has a purpose. This is one we talked about before. Remember we talked, when I did Blinky, I talked about location 90. That's port 1, right there. I also have in that there, we also have some other bits, locations along here that are bit addressable. Now, all these names, you don't have to remember their locations, because as you recall, we did an include file that, we included a file called C8051 F850 or something like that. That actually specified what all those are, right there. But as we look at some of these right here, these are bit addressables. These are not. This column here is bit addressable. I got that messed up here. Up there. Everything in this gray one. So P1. So I can look at P1.1, for example, and that's bit 1 of P1. I can look at P1.0. I can look at individual bits. Right here, P2. This up there. Each one of these. This is our timer control. Now we also have along here. These are also special function registers. So as you can well see, we use up all 128 bytes real fast, right there, right along here. Because if you count this is location 80, 81, 82, 83, 84, 85, 86, 87. Then we come here to 88, right there. So those are the way you would read this right here. So this is 80. So this one is 83. This is C0. This is C3. Right there. And then when you go across the top, right, where it starts with C8, this one here would be CB. Because you get the B from, if it starts with a 8, then you read the one in parentheses for those locations. So what we've got here, let me just kind of point out a couple of them here. Let's just look at this one right. Let's look at these two right here. Right here. Look at those two right there. That's TL2 and TH2. What those two locations are is timer 2, the lower 8 bits, and timer 2, the upper 8 bits. Is how that's defined there. So that there. Same one with right here. We got TL1 and these two are separated. Right here, these two go together, and these two go together. Right there. I don't know why they did it that way, but that there. So let me just kind of clear that off there a little bit. So all this is saying is T0 and T0 go this way, and T1 and T1 go here, right there. Right there. We also have a register here. This is our clock control. You can kind of guess what some of these mean. This here is ADC0, high and low. That's a 16-bit. When we read analog digital converter 0, it's got a high and low order byte to it. We also got our control registers for our analog digital converters. This particular chip has some DACs. Our chip doesn't have any digital analog converters on it up there. The 20 has analog outputs as well. Ours does not. So ours may not have all these registers because ours only has 2 ports, for example, P0 and P1. We don't have a port 3 and 4. So this one here, and where's port? These two are not on our chip, right there. So those locations are just not used, right there. So, but these are the special function registers, and if we were to bring up, and I didn't bring a copy of it simply because I didn't want to scare everybody, but if we were to bring up the data sheet that goes with this processor, there's a data sheet that goes with our particular processor. It's about 300 pages long. Mm-hmm.
So there are a lot of short form. I mean, it's like CC, ON, B1, SP. What does it mean?
Which ones? What?
PSW, PCA.
That's what you need the data sheet to figure out. I don't know all these off the top of my head. That's there. Well, I mean, like this one here, AMX. That's analog mux. Yeah, AMX 0. That's analog mux 0, and then we've got 3 different control registers. And without referring back to the data sheet, I'm not going to tell you what those mean because I'll probably get it wrong. As I get ready to say, this 300-page document that I'm not scaring you with goes through each one of these registers in great detail and how to program them for certain functions to do. One that we talked about earlier, in my very first demo program, we talked about this one here. That one there in the upper right-hand corner, that's our watchdog timer control register. That's how we turn off the watchdog timer. and turn off our watchdog timer. We also have probably some registers in there, some bits there where we can turn it on and tell it how many clock cycles before it times out. So that's our watchdog timer register, right, that's there. So then we've got TL4 and TH5, that's our timer 4 data there. EIP 1 and 2, I don't know what those are off the top of my head.
The PSW?
Which?
D0,
D0, that's the PSW. That's the, boy, I should know that. We're going to cover it in a minute again. I just drew a blank on that there. That's our status word, our program status word. Yeah, so if there's a 0, if you have a carry or something like that, the carry bit is included in that there.
Because I found some instruction PSW.
Yeah, that's a program status word, that there. And we'll cover that. That's why I'm drawing a blank what PSW stands for off the top of my head. It's Thursday, that there. And this is my last class for the week, so by this point I'm usually pretty fried, but PSW, we'll talk about that in a minute. And we'll cover that further in the slides. It's covered. Not all of these we will cover, by the way. Some of these are for the serial buffer. If we're using the serial ports, the serial ports are covered by things such as right here. This is our serial buffer right there. So you got to remember when we look back at this chip, it has a lot of peripherals built into it, and these are all controlled with these special function registers. This is what controls everything on the chip. Using the 8051 requires mastering the special function registers and having a clue for them. That there, and a lot of these I can't tell you off the top of what they are off the top of my head, simply because I've used them and I look them up in the book. And I am not joking. It's about a 350-page book that goes in, and it'll spend 5 pages describing how to set up one particular register, different modes. That there. Okay, we'll get back to some of these here, but there, as we get into some of there. That was just basically an introduction to the memory map, how the memory is outlined within this particular chip. Understanding how the memory map works helps you understand where you can put code, how much code you can put, how you can that there. Now, as we look at the addressing mode, there's 8 different addressing modes, and these are examples of similar to what I've given before. The first one is a register addressing mode. We're using 2 registers, A and B. I mentioned B is one of the registers that's up in the core. That's our only one that's real easy to register because it's right there. It's very fast. Our direct is that 30 is we're moving A, the contents of A, into memory location 30. Indirect means we're going to move the data that's pointed to by R0, that there, into A. So we have an address there is what that is. But the address is stored in A0 or R0. So we place the address there and not the data itself, that there. So R0 in that particular case there. The immediate one is very easy. We put the number sign there, and we're just going to move the number 80 into A. And next week's lab, hopefully, some of you were here when we were talking about getting the software installed. We're going to go through it, and we're going to do examples on each of these so we can see what's happening in memory right there. We're to the point now we actually need to start doing some things on the board, and I need to talk less. That's there. That's there. Which symbol is that? This one here? The ampersand means the address means memory location stored in R0. The number sign, or the hashtag means immediate data. Yeah, it means immediate. Right there, right there. And as I said, we'll go through it, and you can see that when I do this instruction, the number 80 is going to go into A. So I need to write up a series of lab tests where you go through and you write these instructions, and you single step through, and you can look at the memory and see what's happening in that there. these 4 down here are actually used predominantly for branching instructions. This is a short jump ahead, an absolute jump, a long jump, and this is actually, no, this is an index. This one's a combination of multiple ones. This says move into A, whatever sort of address A plus the program counter. Right there. Right there. And we'll see there's various versions of that. So these are our 8 addressing modes. Right there. We have an example on each of these right there. The register addressing involves between registers. It doesn't leave the chip. That's there. Now, all this is going to do is it's going to take the contents of A and move it into R0. Now, R0 can be one of 4 locations because we have a register bank that's 1, 2, 3, or 4, or 1, 2, or 0, 1, 2, and 3, and you have to specify what that bank is. If you don't specify it, it's going to go to bank 0. Right there. So when we look at R0 through R7, there's actually 4 sets of those, and we would set the bank for each of those right there. Direct addressing means now this particular address right here, P3, is actually a memory location. Memory address. Right there. P3, is port 3 on the chip, but it's actually the way that the processor treats it as it's a memory location. And the memory location is P3 is B0. Is B3. So this instruction right here, I could write B0H and it does the same thing right there. So P3 is actually replaced when we write our code. If you look at the binary or hexadecimal code, after it's been assembled, you will see that P3 would change to B0. Right there, only not in our case because we don't have a P3. But you'll be replaced with P1, which was 90. Right there. So direct addressing, you supply the address of that there. So this means the contents of RAM location 20 is moved to the accumulator right there. Indirect means that here, store the contents in the memory location pointed to by registers should have an 8-bit address. Now, because this is an 8-bit address, keep in mind that we're only addressing up to this area right here. Right there. So, and that's the reason why we can get away with only having, right here. That's why we can get away with only having an address for one register to contain the address, because static RAM, as the 8051 is defined, only has 256 bytes. That's all it has, is 256 bytes. That's there. And of which 128 bytes of that is gone because we're using it for the special function registers. So we only have 128 bytes to play with when it comes to the move instruction right there. So memory is fairly tight until we use the MOVEX later on, right there. So again, MOVEX right there. Now the data pointer now has a 16-bit address because that's now addressing that external memory. So we have two different move instructions. Move uses the 128 bytes we've got available on the chip. The MOVEX uses that memory that is on the chip, but we're treating it like it's off the chip. That external memory inside the chip that I talked about, that whatever it is for our chip, 2.4, it's either 2.4 or 8K. I'm thinking our chip is 2K, right there, because we have a small chip. But that goes back to the MOVEX command addresses this memory down here, right there. The move command addresses this memory right here. So we've got two different moves, and we'll go through the moves a little bit more detailed when we look at that there. But move has two flavors, MOVEX and move. MoveX is talking about this external data space right here, right there. And move by itself is talking about this data right here, right there. Now, again, that's at 256 bytes. We could put into right here, for example, this one here, we could put into R0 990, which is the address for port 1, and we could say move at R0, comma A, and that will move A to port 1. The only reason it works is because we loaded the R0 register up with the address of port 1. Right there. So as you look at all these addressing modes, my first reaction was why so many? But then when you start looking at the way the compiler does things, and you start writing, then some of it will make sense, why you have some there. So, we probably won't use but a few of these in our labs, because we're going to be moving to C, and we'll let the compiler worry about setting these things up out there. But the MoveX is now going to the outside memory. It's really the point I was trying to get across at that point there, is that MoveX is set there. And when we use the MoveX with direct addressing, and we'll look at that, we have to supply it a 16-bit address right there. So, okay, immediate constant addressing. Again, that just simply means you put the hashtag there, and we're going to move the number 30 into the accumulator. Here we're going to put in here the number FE00 into the data pointer. Is what we're going to be putting into that there. The hashtag, or and I still refer to it as number tag. I don't know when it started getting called the hashtag. I think that was when Twitter came out. They started calling it the hashtag. That there, because of the ampersand, which is used to be the at. That is what the ampersand used to mean. At. The hashtag used to be called the number sign, and the little at, for addressing, it's kind of at that there. Used to be called the ampersand. That there. So they changed some of these that there. But all this is simply, if you see the number sign or hashtag, that's immediate data. If you see the ampersand or the at there, the A with the long tail, that means that you're talking that register holds the address of where you're looking at. That's indirect addressing. That's there. Relative addressing is where that's there. And this here, you really, really don't get too much into detail there, other than the fact that you have an instruction called, a short jump or conditional jumps. You're limited to jump either 127 bytes ahead or 128 bytes behind. Now, what I typically tell people is you start off with using the short jump, and then if the compiler comes back and says it's too far, then you change it to an absolute jump. If that doesn't work, you change it to a long jump. That's there. Now, this is a limitation of this processor. You won't address it in this class very much, but it does create a little bit of a headache in the term that the conditional jumps are all short jumps, which means we can only jump ahead or behind about 128 bytes. That's there. So that's there. But here's an example here is this is just a simple delay loop. We loaded A up with some number. We decrement A by 1. And then the next instruction is jump not to 0 to location go back. Now go back in this particular case, and this is recording, I need to jump down here. Go back is a label. Right there. Right there. It's a label. That's there. And it can be anything you want. That there. In other words, go back is not a reserved word. The programmer made that term up. And this just simply says go jump, if not 0, back to this location right there. That's all that says. Or jump if not 0. Now the compiler or the assembler will replace that with -1. right there. Because what it's going to do is this here, this jump not zero, it's going to look at the program counter and see how far back or ahead it's supposed to jump, and then just put that number in there. So in this case, we're supposed to go up one instruction. So go back, it's actually going to be -1. It's what it's going to be when you assemble that, because we're going to go to the previous instruction that there, place in memory, or instruction that there. If we have 4 or 5 instructions in between, it might be another number right there. Or if we're going to go ahead, it'll be a positive number. So, but this will be replaced by a number. And that number is the number of bytes either behind or the number of bytes ahead where you want to do the jump. So the assembler actually replaces that with the number right there. So the destination address must be between -128 or +127 because it's an 8-bit offset that there. But that's relative. So it's relative to where it's at now. That's why it's called relative addressing. Absolute means that we can jump within 11 bits right there. So that means that we could go 2K ahead or 2K behind, right? Or actually there within the current 2K byte page of the program memory that there. So it's got to stay within that 2K page essentially, right there. And keep in mind that our program memory is how big on this thing here. It's not very large, right there. That doesn't sound good out there, does it? Our program K is flash memory. It's about 2K is what it looks like out there. So, right there. So we've got our relative. That's got to stay within the same page. Again, you're not going to worry so much about this. This is going to be replaced with the lower 8 bits or lower 11 bits of location port init. Init again is a label that we put in our code out there, and we just simply call. Now this is a call instruction, which means that we're calling a subroutine, which means it probably should have a return at the end of that routine. Right there. When we write C code, we'll see that it will be placing these addresses there. So this gives us 11-bit addressing mode there. A long means that we specify all 16 bits of the address right there. With 16 bits means goes anywhere within 64K of code space, and we just specify the actual address right there. Right there. So this again is a long call, so that's calling a subroutine. So we've got the absolute call, which means we're staying within 2K. A long call, we can go anywhere we want. That there. And you got to remember that they came up with a lot of these additional modes of addressing to try to save space. If you're going to do a short jump, then a short call. If you're going to do a medium size, you do an absolute. And if you're going to do a long jump, then you use the long call or jump right there. So index addressing, this is probably the most confusing one right here, is that, and this one requires that you use the accumulator normally. We load A with the offset 8. We load the data pointer with the starter of our lookup table, and then we say move into A whatever is pointed to by the contents of A plus the data pointer. So this is going to get from memory location 0F08. Whatever's stored there is moved into A. Is moved into A. Right there. Whatever is stored there. Because this puts 8 into A. This puts 01F00 into the data pointer. This is going to move into A. Whatever 8, the 8 is right here. We add 8 to the data pointer. So that gives us memory location 1F08, and that's moved into A. This is a very complex addressing mode. Because your address is split up into 2 parts. One part of the address is contained in the data pointer. The other part is contained in the accumulator. and you add the two of those together. And keep in mind that the data pointer is 16 bits wide, right there. So this allows us to up there. And this is typically used for lookup tables. It's where you would typically use something like that. All right. Moving on, we get into our instruction types. And we're not going to spend a lot of time on these because they're all fairly basic instructions that we have. The 8051 doesn't have very many instructions, and they're not very complex. This is all our arithmetic. We'll start with the arithmetic instructions first. And they're broken up basically into really 3 or 4 groups. The first group right here, these are all add. The only difference is, as you look at this, is the type of memory addressing we got. The first one is using register addressing. The second one is using direct memory. The third one is using indirect. The next one is using immediate, and that's it. You got four addressing modes right there. So you can add to the accumulator 2 registers together. Now notice that the add always ends up in the accumulator. That's our main register. The next set of 4 are exactly the same. The only difference is they add in the carry flag. That's there. So we add the carry flag to it as well. And why would we do that? Is if you're adding 2 numbers together, because you can only add 16-bit or 8 bits at a time, and you want to add a 4-bit number or 4-byte, or a 4-byte number, which is 32 bits. You add the lower 4 bits, 8 bits first, then you add the next 8 bits. But when you add the next 8 bits, you have to include the carry from the previous add. Then when you add the next 8 bits together, you have to include that carry. So it allows you to add a 4-bit number or a 4-byte number together, and in doing so, you have to carry the flag up there. Now, I should point out that there is no instruction for adding 2 4-byte numbers together. So if I gave you a lab assignment, you would have to write the code to do that. And it would require 4 different add instructions. That's there. And that's a very simple program that you'll probably see in the next 2 weeks, probably right after the break, where you're going to be adding 2 4-byte numbers together. That's there. So it's fairly straightforward. But the assignment will look something like this. You've got stored in first thing you're going to do is I'm going to have you store the 2 locations in a couple of memory locations, the 2 numbers, add the 2 of them and store it in a 3rd location, right there. So it's a fairly straightforward that there. So we also have the subtract. Now the subtract always takes into account the carry flag. That's there. So we subtract 2 numbers from each other, and we also subtract the carry flag from each one. Because again, when we subtract, we want to do a borrow. So you subtract in the opposite direction. In the same direction, least significant byte first. And then if you have to borrow, the carry flag is set so you know that the next 4 bits you have to do a borrow right there. Again, today I'm not getting into actually writing the code. We're going to be seeing that right after the break. We'll actually start writing some code here. That there. We've spent about 6 weeks just getting to the point where we're getting to the meat here. All right, the next 4 instructions are just increments, followed by decrements. All they do is they're simply an add with a +1. And you can add to anything that you can address. So we can add to the accumulator, increment A, right there. We can add to a register. Remember, we've got 32 registers set by our banks, right there. We can give it a direct memory location. We can add to a memory location directly, which means that we can add to a port directly. We can look at what's on port 1 and add 1 to it and increase it. There. We can also place into a register a memory address and add to it as well. And everything we can add to, we can also decrement from. So we've got decrement right there. The next two instructions are multiply, and we multiply A and B, and divide A and B, right there, A by B. And the multiply and divide have to use A and B, the registers. You can't use, those two registers. You can't use memory locations for multiply. And then the last instruction here is our decimal adjust A. And what that simply does is if we added, say, two numbers, and I'm just going to write over here, if I can keep from doing that. The problem is the little Windows button is right there on the edge of the screen. I touch it with my knuckle as I go to write on the screen. It's so unnatural to write. That's why my handwriting is so bad. It's not good anyway, but that's there. But it's unnatural because I can't touch the screen with my hand when I write. That's there. So, but if I want to add the numbers, say, and these are decimal numbers, base 10 numbers. So let's say I add the number 37 to 45. Now when I add those two numbers together, that's going to give me 1282, right? That's the right answer, correct? But when I add them in binary, what do I get? 0011, 0111, 0100, 0100. We add this, and we got it. Let's see. This one here is wrong. This is no. This is 5. This is a 1 right there. Yeah. Right there. This is 1, right? 1010 there. So when I add those, I get a 0. I carry a 1. 0. I carry a 1. I get a 1. I carry a 1, and I get a 1 there, right? I get 1110. So 0. So I've got 7. I'm just drawing a blank right here. That looks like 7C, right? So that's 7C. Well, 7C is not a valid number, right? Correct? So if I add another 6 to it, so if I take 7C, 0111, 1100, and I add to it 6 right there, I get 001, 0, 0. That's right. I carry a 1, 0, 0, 0, 1. I get 82. What's that? Oh, I got 5 bits there? Okay, well, regardless, if I had room, what I should do is I should go discard that there because I'm going to go to, let's go to something where I've got some room to work here. Where's my OneNote? There's my OneNote. Quick OneNote right there. You can see right there. So let me just do a new page. All right, so the number we were dealing with was what, 45 and 37? 37, okay. So that's 0100, 0101. All right, we got that right this time. 0111, correct? The 0011, right? So when we add these two, 1 plus 1 is 0, carry a 1. 1 plus 1 is 0, carry a 1. 1 plus 1 plus 1 is 1, carry a 1. Right. So 1, 1, 1, 0. So we've got 7C. Now we know that this is not a legal BCD number. We know that that is true. So if that's the case, if we use that last instruction there, that decimal adjust DAA, immediately after our add, the microprocessor knows to adjust this for a decimal add. So it would automatically look at this and see that I have an illegal number. As soon as it says that that's an illegal number, it knows to add 6 to it. When I add 6 to that, I get 0, 1, 0, 0, right? I carry a 1, I get a 0, carry a 1, 0, carry a 1, I get a 0, I get a 1. I now have 82, which is the correct answer. So that's what that command does. It also does it if there's a carry. That there. So, but that particular command is used to do an adjust. It's DA space A. I keep seeing DAA because I'm used to seeing some processors, they don't have the space there. It's just DAA and only works on the accumulator right there. But that does the decimal adjust. And what that does is adjust for the fact that you had an illegal BCD number. That's there. So that's what that instruction does. But that's all of our arithmetic instructions. That's all that we have to worry about right there. So they're simple. They break up from the add, subtract, increment, decrement, divide, multiply, and DA. Our logical instructions are even fewer. We only have really 3 to worry about, and I'm not going to spend a great deal of time going through these in great detail. I can't tell whether it's dark out or not with these windows tinted, all that there. But the first one, it does a logical bit-by-bit AND, right there. And we can AND the accumulator with a register, a memory location, memory pointing to by register, immediate data, direct, right there, where we're given a memory location, and direct with immediate data. So we've got 5 different ways, or 6 different ways we could do a logical AND. And that just does a bit-by-bit AND, right there. Same thing with OR, bit-by-bit. You know, so, and again, an AND is the same thing as doing, you know, they both have to be a 1 in order for the output to be a 1, or if either of them is a 0, then the output's a 0. The OR, either one of them has to be a 1 for the output to, and does it 1 bit at a time, right there. The next group is the OR, right there. Then followed by the XOR. Now the XOR is that if both of them are 1, the output is 0. If both are 0, the output is 0. But if one is 1 and the other is 0, then the output is 1. Right there. It does the XOR function right there. That there. So that there. And then we've got clear, which simply wipes out right there. You know, wipes out there. Complement. All that does is reverse the 1s and 0s right there. And then the next 3 are rotate, or 4 are rotates. And all they do is they shift to the left and move the other one around. It's just simply, all you're going to do is you're going to take a number, and you've got 2 flavors of that. One is through the carry, and one is with ignoring the carry. So treat the carry as a 9th bit. Right there. So if we've got 1, 1, 0, 1, 1, 0, 1, 0, for example, and we do a rotate left, that means we're going to take this bit and just rotate it around, 1 right there. So so all we have to do is just write this way here, 1, 0, 1, right there, 1, 0, 1, 0, and then we bring this one around. That there. If we do it with a carry, then you take that one in consideration in the rotation. Right there. So this is a shift. This is a rotate left, excuse me, right there. And then you got the rotate right. Right there. So all they do is just rotate the bit. Like that there. And there are applications where we would want to do that. Right there. I can't think of any off the top of my head. I've used these, but I can't think of where I've used them in the past. And then the last one is a swap. And all that does is, if A contains, this is A, and it contains 1, 1, 0, 0, 1, 0, 0, 1, all it does is just swap them. It's going to contain 1, 0, 0, 1, 1, 1, 0, 0. It just swaps these 2 around. It swaps the low order nibble with the high order nibble. You know, the nibble is these 4 bits right here become these 4 bits. These 4 bits become those 4 bits. They just swap those that there. These are the logical ones there. That there. So these are These are all our logical instructions right there. Right there. Now we go to our data transfer. Again, we don't have that many of these. Because data transfer basically we're moving things around, data around. So we've got the first group there is our move, and our move is basically looking at the data on the chip itself, that 128 bytes we've got to work with on the chip. The next two is move code. Remember I said that this chip has a code space, an external space, and an internal space. We have three different addressing spaces that's there. So, and you can look at that, we've got three apartment buildings right there, and each have an apartment 3C that's there, so you have to specify which building you're in. So the first three move instructions refer to building A, the internal memory. The next two move instructions refer to building B, and that's the code that's there. You don't use the code very often, but for example, tax rates. You know, if someone's writing some code for calculating GST, for example, that there, you know, everybody's favorite topic right now, or everyone's least favorite topic. You know, I'm getting ready to buy a little scooter before, you know, to get around the neighborhood when I move, and I pointed out to my wife this morning that we want to make sure we buy it before GST kicks in, right? That there. So, and I'm recording this, going to post that on YouTube, saying that I'm going to buy my scooter before the GST to avoid paying 6% taxes on a 6,000 ringgit scooter, or however much I pay for the scooter, right? That there. But it can't be too small. I'm a big guy. I can't ride a small scooter. That there. But regardless, the GST rate would probably be coded in there, but it would be a variable that you could change when the government decides that 60% is too much and they want to lower it to 5, or they go the other way, they say it's not enough, they raise it to 7. My experience has been with any sales tax in the U.S. that they never go down. So I won't say that that's the case here, but we'll just simply point out that code space is typically, it's stored in the flash memory that there, and you can put data in the code itself that there. It doesn't have to be that there. Now remember that code space data cannot be changed in your program. So you will never see on your move instructions on these move instructions here, where we're talking memory here, these three here, we could move things to the accumulator, right? Or two memory locations right there. And again, not all the possible ones are shown there, but we can have addresses on the left side there. On the move carrots, the only thing you see is the A, because you cannot change code memory within your program. That's part of the ROM or flash memory that cannot be changed during runtime, only during programming time. So anything that's stored in code memory is locked in forever until you reflash the chip. That's there. Now move X, our next series of 4, which is just as versatile right there, that is talking to that external memory outside the chip that we talked about. Only in our case, with our particular processor, it's internal to the chip, but external to the core 8051. Right there. So it's on the chip, but we treat it as external. Right there. Again, we have all of the various variations of our addressing scheme. We've got direct, indirect, indexed, immediate, all those are there. The push and pop deal with the stack. Now, one of the things that you have to set up, if you're going to be using the push and pop, you have to specify where the stack is going to be in memory there, and how large it's going to be. Because if you overflow the stack, bad things happen to your code. There. The stack is a place of memory where you put things temporarily. You push things onto the stack, and you pop things off the stack. And every time you push something onto the stack, it's stored in that memory location, and the stack pointer is moved down to the next one when you push back onto it. When you pop something off, that data is taken off the stack and placed wherever you put it, and the stack pointer moves up. So it moves up and down there. and you only have so many locations for your stack. That there, and you got to be somewhat careful because, especially if you're writing in C and you have a lot of function calls, then you can overflow the stack without realizing it, because the number one thing that uses the stack is whenever you do a function call, it pushes onto the stack the return address. It also pushes onto the stack any variables that you pass to that function. It also pushes onto the stack the return values of anything you've got there. Depending on how you pass variables to functions, did you get into, when you took C, did you get into passing my reference and passing my value? Does those terms mean anything? If you pass by value, you pass the number itself, but if you pass by reference, you pass the address of the number. Did you talk about that in your C class at all? Anybody remember that? I see a lot of glassy eyes as if, I have no clue what you're talking about. Is that true? Well, because when you call a function in C and you pass it a variable, you have a choice. You can pass it the data itself, which means you can use the value within the function, but you can't change it, because when it goes back to the original program, the original data is still there. So you pass it the contents of something, but it doesn't change. Or you could pass it the address of the data, and then if you change it, it changes it in the main program. So depending on how you pass something in C, either the address of the data is pushed onto the stack that you're passing, or the data itself. And you could do it either way. When we start writing some C code toward the end of the class, you're going to find that you could do it either way. But what's pushed onto the stack is going to be either the address or the data itself. If you pass the address, then every place you talk about it in the function, then you're going to be using relative addressing because the address is contained there. If it's not, you're going to be using direct or immediate data. So there's some variations on, and that's one of the reasons why you got so many addressing types, is because when you start writing subroutines in high-level languages, the compiler will use a lot of these. The next three are fairly obvious. All they do is exchange two locations with the accumulator. They just swap the data. Whatever's in the accumulator is moved to the register. Whatever's in the register is moved back. That's why that temp register is needed. There's that buffer right there. This one here, exchange the low-order digits. I don't remember exactly what that does because I've never used that one. I'll have to admit to that one that's there. But exchanges the lower order digits between two registers. I'm not sure where I would use that. I look at that as saying it's just going to exchange the lower bytes. I'll have to look that one up there. I think I skipped that when I talked about this yesterday there. But that's all of our data instruction moves. We're only down to one more left here. Or no, two more. The Boolean variables I won't talk a lot about, but those are just simply bit level operations. You only do things with Boolean variables at the bit level, and they're either 1 or 0. So we can clear a bit right there, clear C. Well, actually, that's the carry flag. We can clear the carry flag, or we can clear with a bit instruction there. C is actually a bit. It's the carry flag within the program status word right there. That's where that P program status word. Now, you asked me what it was, I couldn't remember. Now I just popped it off without thinking about it. That the carry flag is in the program status word right there. So we clear a bit. I think in Blinky we cleared P1.1, for example. That's a bit. We can set a bit. We set the carry flag, or we can set a bit. So we can set P1.1, which turns off the LED right there. We can complement a bit, or that there. And all we do is just, if it's a 1, it's now a 0. If it's a 0, it's a 1. Right there's all that does. We can do a logical AND at the bit level and just AND a bit here, that there. And there's more combinations right there. And this is a kind of interesting one, AND with not the bit. You put the little that there. That one's a little weird. you put the little slanty thing that's there. It's actually not part of going through the instructions, but it's just something you can do. You can put the slash P.1.1, which means invert it before you do the and. Right there. So you've got that there. And you can do the same thing with the or right there. And then we can move a bit by bit. This is variable. It should also mean variable and bit instructions right there. Then the last four are jump instructions, and these are conditional jumps. So I somewhat disagree with, but since I borrowed these slides, actually I didn't steal them since I left Silicon Labs' name on them, that there, and they put them up there for university faculty to use at will. I guess it would be stealing them if I took their name off and put my name on it, pretending that I made them up. That there. But since it's all right to plagiarize as long as you tell where it came from, right? That there. So, and since they're in the business of selling chips, they want to make it as easy to teach their chips as possible. So that's why they do this thing. But these last 5 instructions here are what we call conditional jumps. So all they're saying, and these are all short jumps, so they got to be within 128 bytes, one forward or backwards. That there. And all we're going to say is jump if the carry flag is set. Jump if the carry flag is not set. Jump if a specific bit is set. So I could do a jump P1.1 to check to see whether a button's pressed. I'm assuming a button's on P1.1. I could do a jump if I have a stoplight that's looking for a car in the turn lane, for example. If there's a car sitting on the turn lane, then there's a sensor there that closes a switch underneath the asphalt or in the road. So if there's no car in that lane, I want to jump over the turn signal mode. So I would use the jump, if not set or set, depending on whether it's active high or low, right there. So I can look at that there, and then I can also say jump if a specific byte is set, clear it, and then jump. So in other words, I can clear the carry bit and then before I do the jump. So that's quite often used for interrupt flags, for example. That there. So these are all my bit level instructions. Now it's the last group. We started late, and this is actually going to be one of our longer classes. That there. This is going to pretty much wrap me up here. This last section here. These are our program jumps that there, and these are broken into 2 parts. Right there. At there. The first ones for their deal with function calls. Right there. We've got right here the first 4 here deal with function calls. Actually, this one is a return from interrupt. So anytime you write an interrupt service routine, and we'll be looking at one in probably about 2 weeks, 3 weeks, we'll be writing a short little interrupt service routine. That whenever we're done servicing the interrupt, we want to put a return from interrupt, because that tells the microprocessor that we want to pop the return address back from the stack. And interrupts are handled a little bit different. These are subroutine calls, and we have an A call and a long call. And then just simply, which one you use is really a function on how big your code is. Because a long call means it can be anywhere in the 64K space. If it's an A call or an absolute call, it's got to be within 2K. That there. So it's got to be within the same 2K page. The upper 5 bits of the address can't change. So I've known a lot of people, and I don't have a problem with always using this one here and never using the absolute call. And the only reason I say that a lot of people tend to do that is because you write your code and the absolute call works fine. You add a little bit more code, and all of a sudden you've moved outside that 2K space, and now it doesn't work anymore. Or if you use the long call, it will always work. That there. Because the absolute call works fine. You modify your code someplace else. Those 2 subroutines get spread out. That subroutine gets moved down a little farther in memory when you compile it. That there. And now all of a sudden it doesn't work anymore. So So it's a little risky using the A call. The A jump is not quite so bad because usually that's within the same routine and you're jumping within the same general range in your code. But the calls really depend on where your that they're, for this, so I'm going to call it semester section or whatever you call that, we probably won't write anything beyond the 2K blocks, so you can probably get away with using A call and A jump all the way through and not use a long call. But it doesn't hurt to use a long call. The only thing it costs you is an extra byte and an extra machine cycle. Because you have to process 3 bytes, for the instruction versus 2 bytes for the A call. The A call is actually a 1 byte instruction, a 2 byte instruction. It's a 2 byte instruction because you got 11 for the address and a little, the front part of that is for the jump, the call or the jump command, and then the other 11 bits are for the address. The long call, 1 byte for the call command, and then 2 bytes for the address. So you have an extra byte there. So your code gets a little bit longer, one whole byte. Back when you only had 512 bytes to work with program, or 1K a program, that was a big deal. Now it's not such a big deal with 4K to work with it there. So that there. And then we've got our jump where we do the indirect right there. And this indirect is the address plus a data pointer. You probably won't write anything like that if you're doing it in assembly language right there. So that there actually the jump 0, not 0, the jump not equal, that there, those are all basic instructions where we look at if A is equal to 0, we jump. If it's not equal to 0, we don't jump. Right there. So we've got the short jump there, jump, indirect. Then we've got our compare where we compare A to a register or a memory location or a register to a location or or a memory location to data, and we jump if they're not equal to each other. So these are the jump commands. Remember, we don't have for next loops, we don't have if then else loops, or statements. None of that stuff that you had in C exists in the assembly language. So we use these jump commands to do the same thing. Right there. So that there. So, and that is going to probably wrap up my whole discussion today. Right there. So let me jump in and take the attendance, because before I take attendance, let me stop my recording.